Hey Joe, you ready to do London dispersion forces? Talk about them?
Sounds fun.
Sounds fun.
The name sounds great.
Yeah. You think maybe we should try to abbreviate them?
Yes.
Okay. Well, how should we abbreviate them?
Well, it sounds to me, I guess, just LDF.
LDF. Let's do that.
Okay.
Most chemists actually abbreviate London dispersion forces as LDF, so I think that's what I'm going to do. Okay, so should we talk about London dispersion forces?
I'm ready.
So London dispersion forces, Joe, actually exist here because you have a negative electron cloud. Remember, the electrons are moving all around inside a cloud here, and so all this blue here is negative electrons. Okay, the negative electrons will attract, if you have atoms that are close by, they will attract the nucleus of another thing. And remember, that's a positive charge, so you have a negative and a positive. You have the negative here attracting the positive nucleus. Okay. And so there's a couple of key terms that I'm going to talk about here. Okay, the first key term that we're going to talk about is going to be something called polarizable. Okay, this is definitely a word that you could bring home to your mom and you could wow her with it. She would polarizable. It's a word that nobody knows what it means. But the idea here is that if no other force is present, okay, this electron cloud that's in blue is going to get slightly bent out of shape. It's not going to be perfectly round. And if it's now not perfectly round, you can have a slight uneven distribution of the electrons on one side. Okay? This is what we call a molecule that is polarizable. Okay, it's just very slightly polarizable. So the electrons are found a little bit more over here than they are over here. And so that sets up your negative charge. Okay, as opposed to something that is completely evenly distributed, which there would be no negative charge. Yeah. So here, if there's just that slight misshapenness to the movement of the electrons, you're going to set up your negative charge. And that's what we call polarizable, or sometimes we call it the polarizability. Okay? So the more likely atoms are to do this, the more
polarizability.
Right, the more polarizability it has. Therefore, also the stronger that the LDF is going to be, right? And so not only is this called this idea is called polarizability, but what forms is what we call an induced dipole. Let me spell that right. I can actually spell dipole as opposed to permanent. I don't know how to spell permanent, but I can spell dipole.
Maybe one day we'll find out.
Yeah, that's exactly right. So the induced dipole here is the result of a molecule being polarizable. Okay. So, or an atom. Now, this atom is polarizable and it is attracted to the positive charge, and the nucleus doesn't undergo any of this stuff. It's only the electron cloud that can be moved and shaped. Okay. So, what controls the size of the positive and negative charges here? Well, it's only the negative charges that we really worry about. Well, in terms of polarizability. So, what's going to make that electron cloud more polarizable?
The bigger it gets?
The bigger it is, the more likely it is to be polarizable, right? Because if I have a molecule that is, let me try to erase this stuff here. If I have an atom that has a very small, let me use the right color.
Nucleus?
Has a very small electron cloud. Okay, very small electrons. That means that it can only be slightly polarizable. But now if I have a whole bunch of electrons, this guy can be deformed even more. So it can be more polarizable. So it turns out that the bigger the atom, the more polarizable it is, the more electrons it has. So if you compare something like helium, which has 2 electrons, to something like xenon, which has 54 electrons, okay, this guy is going to be way more polarizable because it has 54 electrons to be able to disrupt it. Okay. Now, not only does the thing with 54 electrons have a more polarizable negative electron shell, but it also has more protons here, so you have a stronger intermolecular force between the two atoms. Okay. Now, you could imagine that this is super, super weak because you're still only dealing with electrons on one atom being attracted to electrons or protons on another atom. So since this is the super weakest force, if something only has London dispersion forces, what state would you imagine that they're going to be in?
So they're going to be in a liquid state?
One below.
Gas.
Gas, right? Because there's nothing holding them together. Even if they get close together, they're still not going to be attracted very much to them.
Oh, okay.
And so they're just going to fall apart and still move independently from each other, right? So it's all about the competition between the stickiness, the force holding them together, and their motion. And so in this case, when it's just London dispersion forces, all you're going to the stickiness is never going to win versus the motion.
Yeah.
So in order for things that are gas to cool down or to turn into a liquid or to a solid, you have to cool it down so much. Because then the molecules or the atoms will stop moving. And so eventually what's going to happen is that they can stick together, right?
Okay.
Yeah.
So when they stop moving, they can stick.
Right. When they stop moving as much.
Yeah.
Nothing ever stops moving completely.
I got you.
Okay. So are there any questions on London dispersion forces and how they work?
That was my question. We just answered it now.
Yeah. Okay. Great. Well, those are all the forces, I guess.
That's a lot of forces.
Yeah. Yeah. See you later, everybody.